Our planet's source of energy is the sun. It is the dominant factor governing our environment, providing the light and the warmth that makes the Earth habitable. It is a yellow dwarf star, like billions of others throughout the galaxies. At its surface, temperatures are around 5,000 degrees Kelvin, but the corona, the sun's atmosphere, has temperatures as hot as 1 million degrees Kelvin. Our sun is a moderately sized star that fuses hydrogen atoms into helium, releasing huge amounts of energy in the process. But this only became clear during the 20th century. For most of human history, the sun has been a mystery, even worshipped as a god. Stonehenge, perhaps the world's most famous prehistoric monument, is aligned so that on midsummer's morning, the sun rises directly over the heel stone and the first rays shine into the centre of the stone circle. Whoever built Stonehenge had no written language, but they had precise knowledge of the path of the sun. The ancient Egyptians worshipped the sun as Ra, the sun god, and the Mayans offered human sacrifices to the sun, while the ancient Aztecs used it as a basis for an accurate calendar. And until the 16th century, it was thought that the sun orbited the Earth. The Earth is an ideal distance from the sun. Our planet enjoys a temperature range that allows water to exist as ice, as water, and as water vapour. This is fundamental to the existence of all life. Warmth from the sun drives weather patterns, the winds, and ocean currents. To learn about our nearest star, scientists use instruments like this one at the Kitt Peak Observatory in Arizona. It is the largest solar telescope in the world. A 2-metre mirror tracks the sun, sending a beam down a shaft extending 100 metres below ground. The result is a unique high-resolution image of the sun, almost 1 metre in diameter. Dr. Stephen Duval hopes to get to the causes of solar activity by determining what's going on in the sun's interior. The goal is to be able to predict some of the phenomena associated with solar activity that are troublesome to us on Earth. Most of Dr. Duval's work is done in this 25-metre-high solar vacuum telescope. Again, mirrors are used to reflect an image of the sun down into the instrument's control room. Here, a daily map of magnetic phenomena on the sun's surface is produced. Nearly all forms of solar activity, from sunspots to solar flares, create magnetic fields. If these disturbances are strong enough, communications on Earth can be disrupted. At NASA's Marshall Space Flight Center in Huntsville, Alabama, Richard Hoover, an astrophysicist, studies the sun with X-ray telescopes. This mirror was part of an instrument used on Skylab to produce solar images. Today, Hoover and scientists from Stanford University are working with a new generation of X-ray telescope. They are producing phenomenal high-resolution images revealing solar turbulence as never seen before. Some observations can only be made from space, above the distorting effects of the atmosphere. Solar Max was launched in 1980, but an instrument malfunction had to be repaired by astronauts before the satellite could monitor the sun at its peak of activity. When the space shuttle lifted off in October 1990, it carried a European satellite called Ulysses, designed to go into polar orbit around the sun. This gives it a view of the sun's polar regions, something we cannot see from the Earth. Ulysses' elliptical orbit takes it close to the sun every 6.2 years. It is just starting its third orbit at a quiet time. The sun goes through an 11-year activity cycle, and on Ulysses' next pass, it will see our star at a time of maximum activity, with violent solar storms and giant flares. coronal mass ejections blast huge amounts of charged particles across space, carrying shifting electric and magnetic fields. Because the Sun rotates, and the material at the equator spins at a faster rate than material near the poles, the Sun's electrical and magnetic fields near the equator become tangled and complex. Additional complexities originate in the corona. Here the solar wind springs into being and blows outward in all directions. In 1973, Skylab, with an array of solar observational instruments, made it possible to see the Sun across its full spectrum. Skylab made an important discovery about the corona and the solar wind. There are huge rips in the corona called coronal holes. These dark patches are areas where vast clouds of solar wind particles have escaped. The particles move at many different speeds, so that the higher energy particles bunch up behind the slower ones. This congestion snarls the magnetic field lines around the Sun's equator into a convoluted tangle that constantly twists and knots and becomes ever harder to understand. Ulysses physicists are also studying particles that originate during solar flares. Solar flares are the most catastrophic and energetic events on the Sun. The particles they yield have extremely high energy. These high-energy particles explode outwards, leaping from one magnetic field line to another to complicate matters around the Sun's equator even more. At the poles, there is less turmoil, and Ulysses is providing the first ever map of the heliosphere from the equator to the poles. Humanity has always been fascinated by the Sun. As technology developed, people examined the Sun more closely. The first in a series of orbiting solar observatories was launched in 1962 and functioned for 18 months. In late 1995, an Atlas rocket launched SOHO, the Solar and Heliospheric Observatory, toward a solar orbit 1.5 million kilometres from Earth, where gravity from both the Sun and the Earth act equally on the spacecraft. SOHO is providing scientists with a comprehensive study of the Sun. Its 12 experiments, developed by scientists from Europe and the United States, are investigating the Sun from its core outwards to the solar wind. On Earth, we are screened from most of the dangerous parts of this radiation by our atmosphere and the Earth's magnetic field. But during extreme solar activity, charged particles can spiral in along the Earth's magnetic field lines. Solar flares are the most violent manifestations of the Sun at the peak of its solar cycle. SOHO has shown that powerful starquakes ripple round the Sun in the wake of these mighty solar flares. Scientists are starting to get a better understanding of how the Sun is structured. SOHO also monitors the solar wind, providing an early warning when a coronal mass ejection is headed towards the Earth. Heavy bombardment with these particles will have a range of effects. Auroras occur in the northern and southern skies at times of solar storms, the charged particles causing ionization of atoms in the upper atmosphere. Satellites can be damaged and power grids can overload or malfunction. Scientists say it's impossible to overstate the importance of SOHO to the worldwide solar science community. Over the last 13 years, SOHO has revolutionized ideas about the solar interior and atmosphere and the acceleration of the solar wind. We can now see images of the Sun's turbulent outer region, known as the convection zone, as well as sunspots, which actually lie beneath the solar surface. The SOHO probe was only intended to operate for 2 years. After 13 years, it still functions well. The team is keen to keep the Solar Observatory operating at least until the next solar maximum, because SOHO has picked up clues that suggest the next active period could be one of extreme violence. To get a better view of the Sun, NASA has launched 2 new probes designed to work in tandem. Called Stereo A and Stereo B, one is flying just inside and slightly ahead of the Earth's orbit, while its twin is flying outside Earth's orbit of the Sun and slightly behind it. The 3-dimensional images of the Sun can help scientists predict when and how hard dangerous solar storms will hit the Earth. The SOHO Observatory is already providing some information, but the 2 stereo spacecraft will be able to triangulate with SOHO and give a much better view of these bursts as they bud off the Sun's surface. The solar atmosphere gives no clues to help us judge distance. Everything appears flat in the 2-dimensional plane of the sky. Having a stereo perspective makes observations much easier. Knowing where the front of the coronal mass ejection cloud is will improve estimates of the arrival time from within a day or so to just a few hours. These plumes of charged gas are huge, and there will be times when they will engulf one of the stereo craft, enabling it to measure the magnetic field inside the storm. Earth-directed solar explosions tend to happen every 27 days, the time it takes for sunspots to rotate once around the Sun. There is also an occasional 155-day cycle of solar flares. We are still not certain why this is so. An annular eclipse of the Sun was visible on October 3, 2005, in parts of Europe, Africa, West Asia and India, with the width of its path reaching about 200 kilometres. The eclipse started in the Atlantic Ocean and ended in the Indian Ocean, with the maximum eclipse lasting about 4 minutes and 30 seconds. A partial eclipse was visible from an even larger number of countries. Skywatchers in Paris gathered at the city's observatory to catch a glimpse of the eclipse. Wearing protective glasses, the crowd looked at the Sun briefly turning into a crescent. A variety of makeshift modifications were available. Using heavy filtration material, telescopes and glasses were adapted so that people could view the phenomenon without damaging their eyes. It is one of nature's coincidences that the much smaller Moon, viewed from the Earth, appears as almost exactly the same size as the huge but much more distant Sun. Hence, when the Moon is exactly aligned between the Earth and the Sun, we have an eclipse. At the United Nations headquarters in Geneva, an overcast sky made it easier to capture these images of the partially eclipsed Sun. The path of the Moon's shadow across the Earth's surface is a narrow one, and in some places the period of occultation may only be seconds. The small town of Archer's Post in Kenya's arid north came to a standstill in preparation for the eclipse. People coated sheets of glass with soot from small burners to make the heavy optical filters required to protect their eyes. It was not until Sir Isaac Newton devised calculus and was able to mathematically predict the movements of the Moon, the Earth and the other planets that humanity had a means of forecasting when and where an eclipse would occur. Once eclipses and transits could be accurately predicted, astronomers were keen to observe them to refine calculations about the distances from the Earth to the Moon and to the Sun. An eclipse was also the only time the Sun's corona became visible. Experimental verification of Einstein's theory of relativity was carried out during the eclipse in 1919 from the coast of West Africa. Though the cause of a solar eclipse is widely understood, there is still a deep-rooted fascination with the way the Sun can disappear during the day. Eclipse watchers travel the world to view the events that are usually only visible from remote locations. But there are other, more regular solar events that humans have a historic connection with. Every year, during the summer solstice, thousands of people gather at the prehistoric stone circle called Stonehenge. Cheers rang out across Britain's Salisbury Plain as the sun rose directly over the heel stone. The monument is open to the public throughout the year, but the longest day of the year allows people the rare opportunity to walk among the 20-ton stones and touch them. Stonehenge is around 5,000 years old. The alignment of the stone circle means that at the solstice, the sun rises along the line of the ancient processional way, along the avenue and over the heel stone. The origins of the ancient monument are shrouded in mystery. It was known to be used by the Druids, a pagan religious order dating back to Celtic Britain, but it is not certain that Stonehenge was built by the Druids. What is obvious is that the ancients who built it had a precise understanding of the annual movements of the sun, though there is no agreement as to its actual purpose. Another festival, at the Aztec pyramids in Teotihuacan, marks the spring equinox. Every year, thousands of people flock to the Pyramid of the Sun, the largest stone pyramid in all of pre-Columbian America. According to Aztec law, they come to purge the icy winter season and receive the sun's energy that arrives with the start of spring. Many Mexicans are intensely aware of their links with traditional Aztec society. They see it as the cornerstone of Mexican culture and something that should be passed on to the next generation. It is customary for people to raise their hands to catch the sun's warmth. Building of the Pyramid of the Sun began in the year 100 AD. It measures 225 metres on each side and is about 65 metres tall. Participants climb up and down the 264 steps of the Aztec monument. People queue for a shaman to conduct a spiritual cleansing with leaves from Mexico's perul tree. The Aztecs had an accurate solar calendar. The 365-day year was divided into 18 months of 20 days, plus 5 extra unlucky days. In Peru, near the city of Cusco, a traditional Inca celebration marks the shortest day of the year, the start of the planting season. Known as Inti Raimi, the Festival of the Sun commences in the temple of Coricancha. On this occasion, the chief ceremonial role was assumed by Professor Americo Ortiz de Ceballos. The festival has its roots in an ancient Inca ceremony which honoured the sun god, Viracocha. The Inti Raimi symbolises the union between the sun and the human beings. The festival was the most important of the Tuansuya Empire, which based its religion around the sun. According to the Pacha Unachak, the calendar used by the Incas, June 24th was the winter solstice and the Inca New Year. After a meeting between the head Inca and the mayor of Cusco, the ceremony culminates in the ancient stone fortress of Sacsayhuaman. Such ceremonies are modern approximations of a tradition that no longer has its religious or agricultural significance. Nonetheless, Inti Raimi still ends with a blood sacrifice. Another ancient tradition connected with the sun that has been revived and adapted to the modern world is the Olympic tradition. Several months before the Olympic Games commence, a flame lighting ceremony takes place at Olympia, the site of the ancient Olympics. 18 priestesses take part in the ceremony, which commemorates the theft of fire from the Greek god Zeus by Prometheus. During the ancient Olympics, a fire was kept burning throughout the course of the Games. The fire was reintroduced at the 1928 Summer Olympics in Amsterdam, and it has been part of the modern Olympic Games ever since. This brand new tradition employs a parabolic mirror to focus the sun's rays to light the Olympic flame. This particular lighting ceremony required a few modifications. TV actress Theodora Siakou, in her role as High Priestess of the Flame, carried with her a traditional Olympic flame ignited by the sun's rays on the previous day. The torch relay of modern times, which transports the flame from Greece to the various designated sites of the Games, had no ancient precedent and was introduced by Karl Diem at the controversial Berlin Olympics in 1936. The ancient Greeks celebrated the first Olympic Games in 776 BC, and the tradition continued for 1,000 years. During the Games, a truce was called to allow all contestants to travel freely from around the Mediterranean to this site at Olympia. Though Theodora called on Apollo, god of the sun and light, to send down his rays, a cloud, courtesy of Erebus, the god of shadows, messed things up. The gods could not bring out the sun to light the torch, as tradition dictates. But long experience meant that the high priestesses had seen this type of thing before, which is why they had a pre-lit flame with them. The torch was lit and tradition was complied with. This particular torch lighting ceremony happened on the verge of winter, before the Winter Olympics in Turin. But the priestesses, at a sun-drenched rehearsal the day before, had lit the flame by the rays of the sun in accordance with the modern Olympic tradition. The sacred flame of friendship was ready to go.